So the question we want to ask and study right now is that if you try to mix different kind of paint color together, you are going to see a brown instead of white color. So this brown is more close to the dark one or the black one, but it is definitely not the white one. So I already give you one trivial explanation is that this kind of combination of color is for the light only. But this kind of combination of color is for the pens and inks only. So this is a primary color and a secondary one, but they are not for the second category of the things. So how does the thing works is that the color of the surface depend on what kind of the light was reflected. So if you try to paint the surface with a red paint color, so what happens is that if you have the light source produce a white light hit on the surface, you will find out only the red light will be reflected. And this is a light actually enter to your eyes, so your eyes will tell you, okay, now the surface looks like the red color. But if you try to paint the surface with, besides the red one, also with the green one, and also with the magenta one, then you will find out the final color will be brown or black. So what does it mean? It means that nothing was reflected. So you cannot even see any light reflected to your eyes, so the surface becomes dark. Now let me use this very interesting example you can see definitely in your daily life as examples. So when you try to print the color photography, so ideally you're printing something, it means you're going to paint the surface with different kind of color. So for the same scenario, now if you only try to print the photo with the magenta color, this is what you're going to see. Another surprise to you, yeah? And because the secondary color is made of the magenta, cyan, and yellow, so you can also choose to print the photo in terms of yellows only. So not a surprise, this is what you're going to see. And C is for the cyan. But now, what it is interesting is that for the scenario D, you try to print them with a combination of the yellow and the cyan. So you are going to see this one. And now, if you try to print the photo with black only, this is what you're going to see. And finally, when you try to combine the magenta, yellow, cyan, and black, and you're going to find out this is the true color you're going to see. So depending on what kind of paint color was provided, you're going to determine that the color reflected to your eyes. So which one is the true color? Who can say that? So now we're just talking about the reflection, which is because of the coating, so it is due to the reflections. But how about the transparent object? So the color of the transparent object depends on what kind of color is allowed to pass through. So you can see once again, this is a glass, it looks blue. But why it looks blue? It is because the light source with white light passing through. But the part with the red light, orange, yellow, green, violet, all reflected. Only the blue light can passing through. So the light looks bluish. So this is how the color of the transparent object is determined. So I hope this sounds trivial to you now. So now I want to study several questions. I'm not sure when you was a kid, have you ever think about that? First, why is the sky blue? So you can consider that the sky is transparent object. If not, how could the light or the cosmic ray enter into the surface? Yeah. So why the sky looks blue? So the hint is, you know that within the sky, it is made of the nitrogen and some of the oxygens. So the answer is that the blue light in the white light, it is at the wavelength which was scattered a lot by the nitrogen particles. So let me say in the other words is that, which means that the wavelength carried by the blue light is actually is in the right size to interact with the size of the nitrogens. So when the white light enter into our atmosphere, only the blue light will interact frequently with the nitrogens. So, which means that only the rest of the frequency of the light can transmit it, but the blue light will be scattered around in the sky. And that's the reason why eventually the sky looks blue to you, because that is the color transparent to that. So let me make a corrections. The blue light is not transparent light for our sky. Instead, it is the frequency of the light will most scattered. So here I show you that a comparison. The probability of the scattering between the blue and the red is about 4.3. So which means the blue light has a frequency 4.3 times more chance to be scattered. So that's the reason that the blue scattered light is what predominate in our visions. And that's the reason our sky looks blue. It is not transparent to the sky. So now the next question is that why is the sunset red? So you can use basically the same principle. So the color of the sky is mainly because of that it is dominated by the blue color. But the color of the sunset is actually from the light, which is not scattered, which will enter into our eyes. Yeah. So we have learned that the blue light was scattered out, most of them. So which means that when the light from the sun enter into your eyes during the sunset, it is mostly composed of the blue, the red, and the orange and yellows. So that's the reason the sunset looks red. But someone will immediately argue that no, during the noontime it is not the case. And you are correct. So here I show you the figures. This is the position of the sun at the noon and the sun at the sunset. So you can see that our layer here is atmosphere. So during the noontime, the light from the sun will penetrate through the atmosphere. So there are some scattering of the blue light. But because of the path is shorter, so not all the blue light was scattered out. However, during the sunset time, you will find out the light from the sun will passing through much longer path to reach to the surface. So the longer the path, the higher the chance the blue light will be scattered out. So that's the reason the color of the sun looks different depending on the time of the day. And during the sunset, it is because of this. And how about the true color of the sun? So you can see that it really depends on the day of the time, which is related to the path the light travel in the atmosphere. So the color of the sun actually depends on the temperatures of the surface of the stars. So there are a bunch of the stars, but they have different kind of temperatures. So the higher the temperatures, the color will be more bluish. And the lower the temperature, the color will be more close to a reddish. So here I give you an example that our sun looks more close to a yellow color. So the surface temperature is around 600 Celsius. It should be Kelvin. And for the famous Orion star, it is much hotter star. So it looks more blue color to us. But the Orion one, it is a star with much lower surface temperature, so they look more red color. But how does these temperatures affect the surface color? It is because the Weyer's law. So you can see there's a distribution here of the power. So this power actually is related to the frequency of the light emitted outward. So the peak frequency here, for this point, the peak frequency is determined by the constant multiplied by the temperature of the surface. So apparently the higher the surface temperature, the higher the frequency, and the higher the frequency, you are going to see a blue light or the violet light instead. So that is how you determine the color of the sun or the color of the different stars. So finally, I'm going to ask a question is that, then why are the clouds white? So here is a tricky one. So the cloud is different from the atmosphere, but it looks white. what happens? It is because the water droplets are considerably larger than the individual molecules, like nitrogens or the oxygens. So their behavior is very different. So in contrast to the scattering that occurs among the tiny particles within the nitrogens and oxygens, water molecules in the air, they mostly refracted and reflected the light of all colors equally. So that's the reason that the net result is a white color, because the probability to be scattered out, to be reflected, are the same. So now the dominant color for the cloud is a combination of all the frequencies again, which is still a white color. So now let's try to a very interesting concept. It is about the rainbow. Why do we see the rainbow? Actually, the rainbow is due to the refractions and all the dispersions we just discussed before. But this kind of dispersion does not happen always. It really depends on your position. But what you're required to see the rainbow is that the sun must shine on the drops of water in the cloud or in a falling rain, and the drops will act as prisms that disperse the light. So therefore, when you see the rainbow, you are facing a rainbow, but the sun is always behind you in the opposite part of the sky. So this determines that in what kind of scenario you can see the rainbow. So you can see how the raindrop disperses the light in the figure here. So you can consider here individually it is a raindrop. And this is the light source, the sunlight, which is behind you. So you're standing here, it is behind you. So from this figure, you can see that follow the ray of the sunlight when he entering into the drop near the surface. Here, there will be a refraction happens for each of the water drop, raindrop. So the light will be dispersed, and now you will receive a total internal reflections, which is what we just learned in the chapter 26. So now this is the first internal reactions. Then they will hit the second surface, and this is the second refraction happens, and this is exactly what we see for the dispersions. However, for each of the raindrop, you are only going to see one of the light from each of the raindrop, because you're standing here, but all the rest are point to other direction at angle. You cannot observe that. So if you are standing at a position can only see one color from any one of these drop, how can you see the rainbow itself? Yeah, the answer is that we have a bunch of the raindrop in the sky. So therefore, if the violet light from a single drop reaches your eyes, the red light will be from the same drop. It isn't elsewhere toward to the feet. So to see the red light, you must look at the drop which is higher in the sky. So the color red is seen where the range between a beams of the sunlight and the dispersed light is about 42 degrees. And the color of the violet is seen where the angles between the sunbeams and is dispersed at angle of 40 degrees. So in order to see the highest frequency, violet one, the angle is about 40, and the lowest frequency is 42. So which means that you have to stand in a position with angle looking at the raindrop, and bunch of them will reflect different kind of frequency of them. And first one which are going to reach to you, I should not say the first one, the higher one will be the red one, and the low one will be the violet one. So you are going to see a rainbow at the order which is like this. So the upper layer is red, and now continuously go to the violet. So this is how you see the rainbows in the sky due to the dispersions.